In this project, we explored transformer-based phone language models for intent classification. So, spoken dialogue systems are used by millions of people every day. Phones are distinct and language-independent sounds and gestures, and speech can be transcribed into phones as well as text. We experimented with phonetic transcriptions of speech in the context of commanding a robot. We also explored how pre-training a transformer on a large corpus of Dutch speech transcribed to phones improves performance. Some previous work in this field was a paper, Capsule Networks for Low-Resource Spoken Language Understanding. The authors were able to achieve state-of-the-art on the Grabo dataset using capsule networks. They also considered non-negative matrix factorization and encoder-decoder models, which performed worse than capsule networks. Another paper was improving end-to-end speech classification with Reptile. The authors improved model performance with little to no additional data. They also improved pre-training results, but the metrics in these papers were different from ours as they directly use speech rather than speech converged to phones. For pre-training, we saw the Common Voice Mozilla dataset and spoken Wikipedia articles. For training, we used the Grabo dataset, which consists of Dutch commands given to a robot. Some examples are move left, open grabber, throttle slowly. We had 11 speakers in this dataset with 36 output labels and commands and 15 repetitions per speaker. For pre-processing, we used Allosaurus to convert speech into a list of phones. We removed all empty phonetic transcriptions as well as the transcriptions labeled as silent. We one-hot encoded the phone data as well as the labels. We have 36 unique labels, one for each combination of intent slots. For our data split, we used 80% for training, 10% for validation, and 10% for testing. Our baseline model was CNN and BiLSTM.
For our BERT model, we had 6 encoder blocks, a hidden size of 128, and 4 attention heads. And this consisted, this was our transformer encoder layers. In addition, we had 2 fully connected layers with nonlinear activations, each with a hidden size of 1024. We also used pre-training, which used a masked language model objective. For some details for our transformer, we used a vocabulary size of 234 with 4 tokens reserved for special characters. We trained the language model similar to how Roberto was trained, where we randomly sampled 15% of the phones from the label phones and replaced this with a masking token. Of those, 80% of the sampled sequences are replaced with a masking token, 10% are left unchanged, and 10% are replaced by a randomly selected vocabulary phone. So the model predicts the masked phones at the corresponding time step. And we use the MLM objective, which is the cross entropy loss when predicting the masked tokens at appropriate time steps. And we also used positional encodings where we added fixed positional encodings to our input phone embeddings and then proceeded to feed this into the stack of transformer encodings. For our training, we used weight tying for our encoder weights. With weight tying, we achieved a negative log likelihood of 2.69 in 80 epochs, and without weight tying, we achieved a negative log likelihood of 2.74 in 80 epochs. We also used an Atom optimizer where we increased the learning rate linearly for warm-up steps, and we set that to 16,000. And we decayed this proportionally to the inverse square root of training steps with a max learning rate of 2e negative 3. So as you can see, our best model was the transformer with a pre-trained language model with weight tying, and this achieves an accuracy of 90.01%. So in conclusion, we proved our hypothesis that our model would perform a BERT model would perform better than our CNN plus LSTM model. And this has the potential for multilingual transfer learning, which can be used to create speech systems for under-resourced language.